Finally. Sorry for that delay because obviously you're already looking for a short coffee break. So first disclaimer, my presentation will be short and I will end it with questions in order to prevent your questions. And the second one, as you can see, I'm from Faculty of Biology. But my primary field of interest is biophysics of biosurfaces, and I mean biosurfaces like the cornea of the eyes. So after these extensive days of watching visual displays, you'll be free to consult me if you have some irritations. After that I can begin. I will start with one question, a simple question rather. And that question is already answered for multiple times today. And the question is, what do we need for life to begin? And when we speak of life, of course, we will stick to that a life which is here on Earth. And as you can see, we need atmosphere, we need that beautiful planet, we need the moon, as already explained. We need that moon in order to prevent the Earth from precession, vibration, etc., etc. But is it enough? Is it enough for life conditions in entire universe? I believe not. So let's go back to those three prerequisites of life, as beautifully explained and summarized by John Desmond Bernal. And those prerequisites are the formation of biological monomers, then the formation of biological polymers, and finally the evolution from molecules to cells. And can we think of one more member of all these aforementioned? So one more ingredient here. I can think only of one thing: energy transfer. So the existence of complex life is impossible without this energy transfer, and in modern biology it's quite simple. Of course, it's not a simple thing. It depends on the entire group of phosphorylated compounds like ATP, NAD phosphate, etc., etc. But at the very beginning of life, maybe something else would take care for all this transfer of energy in order to for that energy to be consumed in a controlled way. And this thing is still present in nowadays electron transfer chains, and it is very common. It is common to all the living organisms. It is called iron-sulfur complexes. What iron-sulfur complexes look like? Pretty much like this: a small box of two iron atoms and two sulfur atoms encapsulated in, as you can see, alpha spirals and beta sheets of protein. And of course, here in the room, Professor Sussel can tell a lot more than me about the origin and the formation of iron-sulfur complexes, but nevertheless, before ATP, phosphate, and all that complex system that we know today, of course, there is an entire reaction network of small molecules with carbon compounds, and this is a beautiful article about that from Martin Tower in 2017. Which show you the importance of thioesters, acetyl phosphate, and then already ATPs. And you can see that in the beginning of that chain of events are lying those reduced ferritosides. The proposed mechanism, which I like very much, is that those ferritosides can be formed in Earth-like environments, in terrestrial planets, in the reducing or even slightly oxidizing atmospheres. As you can see, they are ubiquitous. So we can find these iron-sulfur clusters in prokaryotes, in eukaryotes like us in that convolvulum, and also in archaea. So all the living systems, and you saw the biodiversity in those previous lectures, depends on that energy transfer. But in living systems, these complexes are assembled by quite a sophisticated machinery which is called iron-sulfur complex cluster assembly machinery. And it involves like 5 or 6 proteins which assemble together, which transfer the components that finally are assembled in that structure, as you can see it in the middle of the picture. And in the experiments that were performed by Bonfio and colleagues, including Professor Sussel, they also used protein compound glutathione in order to help the transition from iron and sulfur into that ordered complexes, which are crucial for life. So here we come to that question. The formation of Earth is the consensus about the formation of Earth is that it was formed like 4.5 billion years ago. So there is a big debate about the earliest evidence of life, and some speculative articles even put it back to 4.3 billion years ago. Of course, is it possible, I would ask? Because as we were reminded here, Earth's primordial crust was completely destroyed 3.3 billion years ago. So what happened to that first life? What happened to that first life? Because we already have fossilized microorganisms, and we have evidence for such a life for such an ancient life 3.5 billion years ago. So it's quite a small gap in order to perform all those necessary reactions from geochemistry, which eventually will lead us to the biological evolution. And of course it is quite possible here on Earth, but is it possible for all the planets around? And that leads us to, again, to the topic of my presentation, which are the protoplanetary disks. So the protoplanetary disks, we are all familiar with these structures. We have beautiful pictures thanks to ALMA, for instance, of those protoplanetary disks. And let's give it, let's just summarize their anatomy, because you know, I'm a biologist, that's why I can't speak about the structure of protoplanetary disks, I speak about their anatomy. The anatomy of the disk, that is a very beautiful diagram from the Henning-Semyonov book, which is called Protoplanetary Disks Chemistry. I highly recommend it. And as you can see, these are very complex environments. They have an inner part, they have an outer part, they have a photon-dominated rich molecule chemistry. They have all the necessary conditions in order to make all kinds of very sophisticated reactions. And amongst these reactions, let's go deeper and take a look at the structure of already these disks. As you can see, all kinds of reactions can happen here, like neutral-neutral reactions, like photoionization, like gas-dust surface interactions, which lead us to surfaces again. Because life tends to happen on the boundaries, on the surfaces of things. And the surfaces of the dust particles are very complex. We'll come to that later. So let's take a look at quite a brief chemical overview of the possible chemistry in the protoplanetary disks. As you can see, we have possibility of formation of bonds due to radiative association, due to surface catalytic reactions, due to three-body interactions. We have also the possibility of destruction of bonds by photodissociation, by dissociation from cosmic ray particles. Also, we have a possibility of reconstructing bonds. I mean here, neutron-neutron reactions. And we have a possibility to not to change the bonds, but nevertheless produce new products. And it depends on the exact position of the bodies or planetesimals or dust particles in the vicinity of that protoplanetary disks. And just a brief overview of all those compounds which are already detected in the protoplanetary disks. And as you can see here, there are multiple detections. I just pick the more interesting molecules here, and I can emphasize on hydrogen cyanide, which we saw together today, is quite important for the creation of all this necessary machinery for building a living cell. Yes, this is a very important and a very chemically active system. So why not to think of something more complex conceived there? And what do I mean by that? I mean that some biomolecules are detected, and Rosita showed us a very beautiful picture from ESA about that Rosetta Zoo. It was quite more complicated than what I have shown here, but as you can see, we can detect, we have detected the presence of ribose, the presence of glycine, and the presence of glycine was detected in that Rosina mission. Rosina was part of Rosetta mission, and it was detected actually in the Churyumov-Gerasimenko comet. And also, according to Rittmeyer and colleagues, we can detect ferrous sulfides. So we have all the compounds to make critical biomolecules, and it will already set the opportunity for these biomolecules to end up on a forming planet, and let's say not to start from scratch, from building everything on the planet's surface, but to start with already pre-built blocks. And I know that this hypothesis is rather unpopular, so I'm prepared for that. Okay, because this is a very interesting and ongoing topic, as you can see, future survey is planned, and thanks to the achievement of modern observational astronomy, we have now a very distinct map of more than 40 protoplanetary disks. I mean here the Sharp project, and the further projects which are in the James Webb Space Telescope, they will be led, I know that from the website of the James Webb Telescope, they will be led by Colette Salik of SAR College, and they will measure spectra that can reveal molecules in the inner regions of these protoplanetary disks. Regions that are, because of their nature, that are not quite well observed from the Earth, or the possibility of this is not so well developed. And here I have a quite meta idea. Let's build one. let's build a protoplanetary disk here on Earth. And here I refer to the McMaster University planetary simulations. Of course, they have made, maybe they have made it. I don't know if you guys made it, please inform me. But why I think it's important? Because you can see here, that's just kind of things that I think are can be put in this simulation of protoplanetary disk. Because I have read about more than 60 model systems of protoplanetary disks, and all their computer simulation, either with deep learning parameters or neural networks, etc., etc. But nothing can replace a good physical model system. That's my opinion. In order to avoid that ominous spherical cow. So, if you think that it's a hard task or impossible task, what about this task? Because I don't see a lot of enthusiasm here about building a protoplanetary system simulation. But if I tell you that you have to take 800 human-induced pluripotent stem cells to make them neurons, then to plate them, to culture them on high-density multi-electrode arrays, and then to teach them to play a computer game. Is that a hard task? Yes, of course. And Brett Kagan from Cortical Lab in Australia managed to do that. So there are no impossible tasks, maybe hard ones, maybe hard in that present moment, but not impossible. And with that, I want to finish my presentation with those questions that I promised in the beginning. The first question, rather rhetorical: can we accept that life is a unique phenomenon, typical only to the Earth or Earth-like planets? Because we are a little bit Earth-centered, as Didier Queloz reminded us yesterday. We are, of course, we are humans. We are located here on Earth, and that's why we think of Earth as our home, and it exerts pressure on our minds. The second question: is it possible for the formation of complex organic compounds at an earlier stage of the evolution of the planetary system? I believe that there are enough data about that, but still, I'm not certain. And the third question: is it possible to form biopolymers such as proteins or nucleic acids outside the planetary frameworks? In that question, I think it's too big for me to answer and to hope to answer in the future, but that's why we are a community. So, with this, I return us all back to Earth. Thank you for your attention, and waiting your questions. Thank you very much.
So, coming from the planetary science community and from the commentary community, I want to go back to your point where you mentioned that complex chemistry has been observed in protoplanetary disks and to some extent on comets, so we have organic molecules on comets. But this doesn't go in the direction that the field thinks that these could have been delivered to Earth and have helped the formation of life. So, can you and people in the room help me understand, are we diverging as a community in planetary science thinking in this direction with people working on developing models for life synthesis on Earth? So because you said that the field is not going in that direction, and you will be contradicted there. So can you help me understand?
No, thank you for that question. I'm not quite familiar with all of the, because I said in the beginning that I'm kind of outsider of that field. Yes, I understand that the main, maybe it's a wrong impression, but I understand that the consensus today is that life has originated on Earth, and only on Earth we should seek for the building blocks of that life. Or if there is a contribution from small bodies, the solar system, this contribution is not negligible, but not enough to be taken into account. But maybe I'm wrong here. If I'm wrong, I would be happy. Am I wrong? Please tell me.
So I just have a comment, which is in carbonaceous meteorites, there was a paper published by Ober et al. Earlier this year where they found nuclear bases, purines and pyrimidines. So, but that doesn't mean that that's where these things necessarily come from. To me, it means that it's relatively easy to make such biomolecules. And also, earlier, I think it was last year, a paper was published showing that you could make iron cyanide complexes somewhat similar to the active sites in hydrogenase enzymes. And so there's lots of things going on in the reducing chemistry of the solar nebula that regardless of whether that actually has relevance to life, the origin of life on Earth, because you have to deliver those things and they have to be intact, right, when they arrive on the Earth. They're not burned up. But even if that has no relevance to the origin of life directly, it shows that these things are easy to be made. They can be made in abiotic ways. And so I think it's all relevant, but the question of whether life, the molecules for life were seeded from these objects is still one of debate.
That's why, and by the way, thank you for that comment and for that information that I missed about nucleobases found on asteroid. Or you wanted to ask a question?
No, it's just a comment.
Okay, that's why I have put a picture of Cat's Paw Nebula, because it's a region which is highly enriched in so-called polycyclic aromatic hydrocarbons, and we know that there is an existing mechanism from which you can assemble actually something which is very similar to nucleic acids using these polycyclic aromatic hydrocarbons. So, yes.
Follow up from the front row here. I wanted to clear up a misinterpretation that the destruction of the crust, the primordial crust, was by 3.3. So the recycling mechanism just got rid of it. That doesn't mean that there isn't anything bad that happened at that time. No, it's just that the laundry was done.
Okay, so that's my lack of knowledge. Sorry.
Yeah,
geochemistry.
No, it's just the difference between the words by and at.
Okay.
But now, this is interesting about asteroids and small bodies. They seem to have all of the components that we think you need for life, right? Liquid water, energy resources, organic raw molecules, and even the molecules that are particularly sophisticated. Now, I'm sorry?
Parts spectrally.
Parts at low concentration, but then, these things are in parent bodies that are 100 or 200 kilometers in diameter, maybe larger. And they were heated for upwards of 30 million years, but no life you had tens of millions of combinatorial chemists working in little pore spaces in these asteroids. Yet it yielded no life. So there are a couple of conclusions maybe someone could draw from that, because if the ingredients are there, albeit at low concentration. Either it takes more than 30 million years, or a simpler explanation is just not the right environment. It's not a planetary environment where, yeah, the combinatorial chemist over there is making something, but none of the products meet the combinatorial chemist's workbench over here. So because these objects they're actually very porous, but they're low permeability. So the pores are not connected to one another. It's a very peculiar substance, these carbonaceous chondrites. And then delivering this material to the Earth is a problem. Because impact plumes are 2,000 to 3,000 Kelvin. So everything, even sophisticated, all the sophisticated chemistry, goes back to ionic components. It's going to have to be soft landing material, but unfortunately the mass of that coming in is fabulously low compared to the mass augmentation that's brought from the large objects. So that's why we, in cosmogeochemistry, and we want to call it, we throw up our hands and we say the chemistry out there is absolutely fascinating. Lots of gas phase reactions, cold electron temperatures, et cetera, et cetera. But templating that on the Earth is a problem. So I think that explains in part why the eye has moved back down to the ground again. So comments, leaving that open for discussion.
Okay, thank you.
What do you think? Is that a good place to leave the discussion?
Yes, I believe that's an excellent place for leaving the discussion. And I believe that maybe 99% of all of the audience think as I do. So, coffee time.
Thank you. Before you